Now, because the C language itself doesn't define any features to handle I/O, a library evolved long ago on Unix to meet these needs, the so-called Standard I/O library. And even the original K&R book, the Kernighan and Ritchie book on the C programming language, which dates from 1978, describes these routines, and they have long been part of Standard C. So, how do we open a file using the standard library? Well, this is going to look kind of familiar based on what we just learned, but there are some differences. Opening a file uses fopen. The first argument again is just the name of the file, but the second argument here, the mode argument, is now a string. The standard defines various characters that can appear here, and I've just shown some of them. The use of B here to indicate a binary file as opposed to a text file is important on Windows, where on text files line termination characters are processed specially, but Unix and Linux have never drawn a distinction between text and binary files, so the B is actually ignored. Also, the return type, the type of the file descriptor, is now a pointer to file, where file is presumably a type def to some obscure-looking structure in a header file somewhere. To be honest, even after 30 years of programming in C, I've never bothered to chase down the details. It's just an opaque type. Now, in Module 1, we talked about routines returning -1 on errors. Here we meet another common behaviour. Functions that normally return a pointer typically return a null pointer on error. Output using the standard I/O library uses fwrite. It's quite similar to write, except that it introduces the idea of writing a specified number of objects, each of a specified size, whereas write just specifies a byte count. And based on that, you can probably guess what the equivalent input routine looks like, fread. Again, I would stress the importance of taking care to ensure that the amount of data you ask to read does not exceed the capacity of the buffer. And closing a file uses fclose rather than close. But the comments I made before about not forgetting to close files when you're done with them still apply. Let's just summarise some of the differences between the low-level I/O system calls and the calls in the standard I/O library. Sequential read and write access, the low-level calls are open, close, read and write. The standard I/O library calls fopen, fclose, fread, fwrite. For random access, the system call is lseek. The standard I/O library routines are fseek and rewind, though I haven't actually covered those in this module. For a system call, the file descriptors are just plain integers. For the standard I/O library, they are of type pointer to file. Something I haven't discussed up till now, the system calls do not do any user space buffering, and the standard I/O library routines do. I will do a demonstration for you a little later in the module that indicates the performance benefits that this user space buffering can give you. Finally, let me just note that the standard I/O library routines are part of standard C, whereas the low-level I/O routines are not. Now, I want to look briefly at formatted I/O, that is to say I/O where some change of representation occurs between what's stored in memory and the sequence of bytes that gets written to the file. So we're going to look at printf and its friends. Now, printf is widely known. It features in most implementations of the C version of Hello World, for example. And basically it generates a formatted string and it writes it to standard output, that is to file descriptor 1. Now the first argument is a string. It contains a mixture of literal text and format codes that begin with a %sign. The format codes are matched up positionally with the remaining arguments. And the value of the argument is formatted, that is to say, it's converted to a readable text string and written out at the appropriate point in the string. The remaining text is output literally. Printf returns the number of characters that were printed, though in most programs this value is just ignored. Now the man page for printf devotes a lot of space to describing the format codes, and even the C standard devotes 7 pages to the subject. But we are kind of straying from the systems programming path here, so I'll just be content to show you a few examples, so that in the unlikely event that you haven't seen this before, you'll get the general idea. So we'll begin with %d, which says just to output an integer as a decimal value. Here we introduce the idea of a field width. The value will be right justified in an 8-character field. We can specify a negative field width, in which case the output will be left justified in the field. %s outputs a string. And here we have a slightly fancier example. The F format code says that we are outputting a floating point value, that is to say a double in C terms, in a 12-character field with 3 digits after the decimal point. As I say, for the full details of this, have a look at the man page. Now, just before we finish this clip, I wanted to mention a couple of close relations to printf. First, we have fprintf, which takes an extra argument specifying the stream you want to write to. Now remember, this is a standard library routine, so this is a file star type descriptor like you get back from fopen. There's a predefined constant called stderr, standard error. So doing an fprintf to this stream is a good way to output an error report. Not everyone is writing console applications, of course. You might be developing a graphical app, or you might be writing a server whose standard output and standard error streams aren't connected anywhere useful. In these cases, you might find sprintf useful. It works just like printf, except that it builds its string in memory, which you could then use for whatever purpose you wanted, placing it into a text box on a graphical app, or building an SQL query, for example. Do take care about the risk of overflowing the buffer with sprintf. You might prefer to use snprintf, which lets you limit the number of characters that will be placed in the buffer.